Hello, and welcome to a new lecture on Cantera. Today, we will learn about enthalpy and specific heats of species. This is a very important topic and it will come very handy in the future when we work on calculating the lower heating value, higher heating value of fuels and heats of reaction and so on. So let's quickly jump into it. Go to the next slide. So standard enthalpy of formation. I'm pretty sure you all must be familiar with this concept. You must have read this in your combustion class, but we'll still briefly go over it. So the standard enthalpy of formation is the heat that is evolved when 1 mole of a substance is formed from its elements in their standard state, which is 298.15 Kelvin of temperature and 1 bar of pressure, which is 10 to the power 5 Pascal. And on the right, you see this table, which shows you the enthalpy of formation of all of these species. The negative signs means it is an exothermic reaction. The positive means an endothermic reaction. So if we take CO, for example, carbon monoxide, the table says that if you take carbon element and oxygen element and combine to form carbon monoxide, it will release 110.5 kilojoules per mole of energy, and that will be known as the heat of formation of carbon monoxide. So the same thing goes for all of the other species. But if you see, there are 3 zeros in this entire list: oxygen, hydrogen, and nitrogen, which means that when an element is found in a particular species as a standard state. So oxygen in the standard state of 298.15 Kelvin and 1 bar of pressure, oxygen is found as in the form of O2. Hydrogen element is found in the form of H2, and nitrogen element is found in the form of N2 at the normal standard temperature and pressure. Such species are given a heat of formation of 0. And that is why oxygen, hydrogen, nitrogen have a 0 enthalpy of formation. So I'm pretty sure you must already be knowing about these things, but just to recap a bit. Now let's go to Cantera and learn a couple of important functionalities and attributes that will be useful in this case. So we will just work off of the console here because we just need a couple of lines, a couple of commands. We're not writing the whole script just yet. We will do that in the next lecture. Let's go ahead and let me first import Cantera. CT. Let me define a phase. Gas equals CT dot solution GRI 30 dot YAML. Okay. Did something go wrong? Oh, sorry. I spelled out the data file wrong. GRI 30. Okay. Now let's take a look at this phase. Okay, so it has been initialized to hydrogen as we have seen in the previous lecture. Now let's go ahead and initialize this to oxygen, O2, in the standard state. So let's say gas dot TPX equals temperature is 298.15 in standard state. Pressure will be 10 to the power 5 Pascal, and this will be O2. We're just assigning oxygen to this entire gas. Now, if we look at gas, see, everything has been initialized to 100% oxygen. Now let's go ahead and look at the enthalpy of this mixture or this phase rather. So I can write gas dot enthalpy underscore mass. If I hit enter, it shows you the enthalpy in terms of mass units. So joules per kg. This is the enthalpy of 100% oxygen. If you have 100% oxygen in a mixture, which is to say it is pure oxygen, then it will have this amount of enthalpy in joules per kg. This, by the way, is also shown here in per kg, enthalpy per kg. There is also per mole, and you can find that by replacing mass by mole, and see it is the same number. So this number here is joules per mole, per kilomole, sorry, per kilomole. And this number here is joules per kg. So if you see, these numbers are very close to zero. The reason is that, again, you have the standard state of the gas, the thermodynamic state of this gas is the standard state. And at standard state, oxygen has a zero enthalpy. And that is why you see this. Now, if I raise the temperature of this gas by a small amount, let's say from 298.15, let's go to 300 Kelvin. Now, if I look at enthalpy, see now it has increased. All of this increase from 0 to 1698 joules per kg is because of the sensible enthalpy that has been added due to the temperature rise. So that's how you look at enthalpy of any mixture, whether it is 100% pure substance or it's a mixture of 2 different substances or 10 different substances. You can use enthalpy mass, enthalpy mole, and what else? Then next, let's take a look at something else. Similarly, if I can look at it in molar basis, and that's per mole, that's joules per mole, per kilomole again, sorry, per kilomole of enthalpy of oxygen at 300 Kelvin and 10 to the power 5 pressure, 10 to the power 5 Pascal pressure. Now let's do one thing. Let's initialize this to carbon dioxide at standard temperature and pressure. So we go here, instead of 300, we put 298.15 this and convert O2 to carbon dioxide. Now the gas has been converted. The phase has 100% carbon dioxide. Now if I go ahead and look at the enthalpy, let's look at mole. It shows minus 393 507,757 joules per kilomole. Right. Now, if we go back to the presentation, you see here, carbon dioxide has minus 393.5 kilojoule per mole. Minus 393.5 kilojoule per mole of enthalpy of formation. And if we go back to Cantera, you will see this is joules per kilomole. If you convert this to kilojoule per mole, it will come out to be the same as what you saw in that table, which will be minus 393.5 kilojoule per mole. Okay, so all of this makes good sense. It matches. And this is how you can find the enthalpy of formation of any species in Cantera. So you can look at CO2, you can look at others as well from the list, and they should all match. Now, the other part is how to find CP and specific heat values, CP, CV, and so on. So let's look at that. For that, you have a function called CP, CP mass. And this again, if you see here, they've actually spelled it out. Heat capacity CP. This is for CO2, sorry. So if I look at, so 100% carbon dioxide, Your CP, this is a CP, heat capacity. It is 843.81 joules per kg, which is what you have here as well. So CP mass, gas.cp mass gives you this number. Similarly, if I write CP mole, see, this will match this number here, because this is joules per kilomole. And so this way you can find CP and CP for any particular species. And again, you can find CV in a similar fashion as well, which is specific heat capacity at constant volume, CV mole and CV mass. And this again, if you see, should match here. 654 and 28821. So that is how you find CP and CV for any species. And you can do the same for any mixture as well. So if I say go ahead and change the mixture to say 100%, so 50% carbon dioxide and say 50% carbon monoxide. Right? Now, again, I can just write CP, CP mass. And so this is the CP of this mixture, 50-50 carbon dioxide and carbon monoxide mixture. One quick sanity check that I will like to show you is if you have, so you must already be knowing that CP minus CV equals R. That is a very famous relation. So let's take a look at that. So gas.cp mass minus gas.cv. This is for the 50-50 mixture of carbon dioxide and carbon monoxide. Mass. Sorry, let's look at mole actually. Mass may be confusing in this case. We'll have to calculate the molecular weight, and that will be a mess. Okay. So if you see Cp mole minus Cv mole is equal to 8314.46. This is the value of the universal gas constant, which is 8314 joules per kilomole Kelvin. Right. So that is all for this particular lecture. We saw details on heats of formation, standard enthalpy of formation, and specific heat at constant pressure, specific heat at constant volume, and these will all be very, very useful as we go forward. So keep these functions in mind, and I'll see you in the next lecture. Thank you.